So my name is Sarvesh. Hold on, let me start my video. Thanks for the introduction. My name is Sarvesh, and today I'll be presenting some of the work we are doing here at MyRadar to apply convolutional neural networks to the interesting problem of having too much satellite data. And I wanted to thank the organizers again for the opportunity to speak today, and thanks for everyone in the audience for making it to the end of the week and last presentation. So appreciate your attention so far. And my topic today, as I mentioned, is a deep learning approach for intelligent thinning of satellite data. So let's start with some background. I like to motivate this talk with this image here, which is a rather stunning view of our planet. And it's an RGB representation of a multispectral full disk goes east image loop from a couple months ago. This is a geocolor representation, which means you're seeing the true color in the daytime portion of the image, as well as a multispectral IR at night. And so this is a sort of compact visualization that shows you how multi and hyperspectral platforms can give us a unique view of the Earth. And so they provide rich data sets as one of the biggest features of how they are useful and what they are capable of doing. But the trade-off can be that the data sets that they produce can outpace our processing abilities, especially if we're trying to process all of the data on an operational cadence. And so it motivates the question of, can we take advantage of these data sets, but in a way that compresses the spatial and spectral information and still minimizes artifacts that we don't want to introduce into any subsequent processing or numerical weather prediction schemes that would use this type of data? And can we use deep learning, specifically an autoencoder architecture, to perform a nonlinear dimensionality reduction on a high dimensional multi or hyperspectral data set and extract the particular aspects of it that we're interested in? So an intelligent way to thin the data. And so before I get too much into the details, I like to take a step back and from a motivation standpoint, we should definitely ask, is deep learning even a good fit for this problem? And why should we choose deep learning for this type of task instead of existing method? And it's, I think, an important question to consider, since deep learning is a really useful technique, but it's only one of the many tools available for a given task. So it's important to evaluate the trade-offs, especially in the context of improving scientific software. So at a high level, the type of deep learning problem that we're working on is one of extreme lossy compression. And we're trying to get high dimensional satellite data into a very low dimensional compressed state. So we're talking about high compression ratios, which can be, a few dozen to one, a few hundreds to one, or even a few thousands to one compression ratios. And especially at the higher compression ratios, we do know that simpler, more standard techniques tend to introduce artifacts at the smaller length scales that can lead to problems in downstream processing. And so here is a demonstration of why deep learning might be a good choice for this type of problem. And what I'm illustrating here is a figure from a recent journal paper in Atmospheric and Ocean Technology, which is showing on the y-axis the radially average power spectral density, which is akin to like texture or variance in the signal in decibels. And on the x-axis, it's shown with respect to increasing wave number, or that can be taken as decreasing length scale of variability. So going higher on the y-axis, more variability, and on the x-axis, the length scale of variability, with high wave numbers corresponding to smaller length scale features. And the paper here took a deep learning technique to try to super resolution upsample radar imagery. So they took an original radar image that was originally had a 512 by 512 input resolution. They downsampled that into a 64 by 64 image, and that's shown as the original, or so the input into the deep learning resolution by this vertical black line. And the it's important to note here that in terms of capturing the variability in power as a function of wave number, from this initial 64 by 64 input dimensionality, the Nyquist of a spatial sampler is 1/2 of its spatial dimensionality, and the neural network technique was the only technique that retained spectral power down to the Nyquist limit. So it retained spectral power to the sort of theoretical limit of where we'd expect us to be able to retrieve that sort of information from signal processing standpoint. And comparing the deep learning technique in green here, which retains a good amount of power until the Nyquist limit, then falls off. It also, at the higher wave numbers, doesn't introduce ringing artifacts that we see here from bilinear or bicubic or Lanczos resampling. So deep learning is good at dealing with this sort of high resolution, high spectral or spatial resolution data, and performing transformations in a way that does not introduce as many artifacts as simpler techniques. Also, deep learning is well suited for many channel data, which is what hyperspectral data is. And it can be used as a way to create a reduced statistical representation of whatever data you have in a way that you can think about being similar to principal component analysis. So we're using a neural network compression akin to doing a nonlinear principal component analysis and allowing the nonlinear activation functions in the deep learning network to capture the structure and patterns and the nonlinearities in pixel and channel covariances. And one of the main advantages of using deep learning for this case is that it allows for onboard processing because we can take advantage of the large training versus inference computational cost dichotomy. And so doing the heavy lifting training on the ground and the much lighter inference in orbit is well suited for the size, weight, and power constraints that are required for on-orbit inference. And so in particular, machine learning, deep learning inference can be achieved at very low power, and you can, for example, do hundreds of frames per second of ImageNet inference at around a watt of power use. So that sort of implies that for these applications, we can do practical on-orbit deep learning classification inference using milliwatts of power. And that overall allows us to do the heavy lifting to train the model on the ground, and we can update weights as needed, and we can do model inference on the satellite, all within the size, weight, and power constraints at the edge. And next slide is to sort of motivate why we're thinking about the problem in this way. And I think at a high level, at MyRadar, our mission and use case is to democratize environmental intelligence in a changing climate. And we've been bringing our core competencies of GPU data processing, nowcasting, and supplying our users alerts to bear on this problem. And over the past few years, we have also expanded the scope of our R&D efforts. And this is related to actually my training. I'm a spectrometer builder by trade. And before I moved from academia to industry, that was sort of what I did as a day job. And so over the last few years, we have been working on our HORIS smallsat constellation. And HORIS stands for Hyperspectral Orbital Remote Imaging Spectrometer. And we launched our first prototype nanosat in 2019, and the second and third prototypes are slated to launch by the middle of this year. And we're hoping that towards the end of this year or the beginning of 2022, we will have our first science mission ready. And the science mission payload includes a set of hyperspectral imagers across the visible, near IR, and thermal IR wavelengths, and a neural chipset of to perform the neural network inference on board the satellite within the size, weight, and power constraints. And so overall, we're using this type of approach because being able to shrink this payload down into a 1U form factor and not accumulate too much power and be able to transmit data down to the Earth within the bandwidth limitations of this platform require us to be able to do all of these functionalities within a demanding duty cycle. And if we can get on board AI data processing to work, we can get from which it'll enable us to do faster detection and therefore faster alerting, because instead of asking the satellite to show us what it sees anymore, we can start asking the satellite to tell us what it sees, which allows us to significantly decrease the amount of data that needs to be downlinked on an operational time frame. So I've introduced at a high level our mission and introduced at our motivation for why we're doing this. So now I'm going to go into a little bit of the experimental setup and what that looks like for this particular task. And so as a proof of concept to see if this type of approach works for this type of data, we're using GOES East Full Disk Level 2 imagery, which is about 5 terabytes a year of imagery. And so we used a large portion of the 2019 5 terabyte data set for training, and we sampled about 1 terabyte of the 2020 imagery for testing. And so we ran experiments on an Azure NC 24RS v2 VM, which has 4 GPUs. And for this approach, we were trying to see how we could feed data to it from a virtualized blob file system without incurring a lot of computational expense or a lot of inefficiencies. And we were able to do that with reasonable performance. And we used TensorFlow 2.3, the low-level Python API, a combination of the sequential and functional APIs, and we implemented a data generator class for facilitating the streaming data and constructing the intermediate representation in memory from the data that we're pulling off the virtualized blob file system. And in essence, what we are doing is image-to-image reconstructions. We have a 16-channel input image. We compress it down to a high compression ratio, low size latent space, and then reconstruct it and see how well the reconstructed image matches to the input data cube. And for the training itself, we ran between 20 and 100 epochs per run for each of the various types of models we trained. And we did data standardization to normalize the input data set, but we experimented with ZCA or PCA sphering as a pre-processing step and found no significant improvements in results. So we did not do that for our production runs. And as part of the comparison to existing techniques, we compare our results to sort of the standard discrete cosine transform DCT type compression algorithm that's used for JPEG compression that's pretty commonly implemented across different arenas and areas of study. And overall, a DCT transforms an image into 8x8 blocks of pixels that you can see here. And it's a linear combination of these 64 patterns called basis functions. And in many ways, the way this manner of breaking down an image into a combination of basis functions is very similar to the filters that a convolutional neural network might learn. But unlike the discrete cosine transform, a neural network can learn very nonlinear transformations and is not pegged to only learning these specific filters. So as a basic overview of the neural network architecture that we're using, we're using autoencoder architecture, which graphically looks like this. So as input, you have 16 channels in your data cube of input imagery, and they undergo convolutional transformations into a compressed latent space of specified dimensionality. So we can construct a different architecture for the autoencoder to have the compressed representation occupy more or less space. And then that latent space is then reassembled back into the original representation in a loss minimizing fashion that can learn the complex nonlinearities that might exist between spectral channels or within the spatial image itself. And this type of network is a fully convolutional network, which means each of the steps is a convolutional layer, and we don't have any dense layers, which makes it agnostic to input dimensionality. It's really helpful for the training to inference jump, because it means we can train it on patches of images, and then we can test it or run the inference on the entire image. And so we also employ residual local skip connections, but no big connections between layers of similar dimensionality like you'd see in a UNet, because that would sort of defeat the purpose of forcing everything to go into this latent space. And then for regularization, we use batch normalization and dropout to help with the interlayer activations being regularized and to prevent overfitting. And so here are some of the basic results that we are able to find with this type of approach. So we take an input image. So this is a single channel tile of a GOES data for visualization for presentation here. It's just channel 6 if people are interested in what specific wavelengths we're looking at here. And this is just taken from a total data cube reconstruction. And for a factor of 32 to 1 compression, here's a typical result from the neural network. And so we see it reconstructs the coarse features pretty well, but the fine scale details are not as well picked up, because with a mean absolute error loss function, the neural network is not incentivized to learn the finer structure. And comparing that to the DCT, the standard JPEG compression, at this low of a compression level, and 32 to 1 in for our use case is considered low compression, both techniques produce comparable mean absolute error values, but the DCT does a lot better with preserving finer structure, but it does introduce significant artifacts that make local gradients. If you were to put this into a numerical weather prediction model, or you're interested in smaller features of interest, you wouldn't be able to trust the local gradients in here. And if they were too large and could make your model blow up, that could be a problem. And so we can visualize what that looks like, again, with one of these radially average power spectral density functions in decibels versus wave number. And this is sort of in normalized units, so I can show you different examples from different input resolutions. So basically, texture is a function of the y-axis, and spatial resolution, granularity is a function of the x-axis. And the original is shown in the blue line. The loss of power and the visual blurriness is indicated by the green line appearing below the original blue line in the spectral power, and the additional power at low spatial length scales or high wave numbers that's shown in this orange line. Basically everything between the blue line and the orange line, where the orange line is adding power, is sort of spurious power or generated from the artifacts that we see. So one of the ways that we can mitigate that for a more apples to apples comparison for the DCT and neural network is to apply a Gaussian anti-aliasing filter, which is sort of the minimum amount of anti-aliasing that we need to bring the spectral power down back to match what we saw as the sort of physically consistent. We don't want any additional power compared to what the original showed. So if we now look at the results having the neural network 32 to 1 compression, the non-anti-alias DCT, and then the anti-alias DCT, we see that at this compression ratio, at this low compression ratio, the finer scale features are still jumping out a little bit better in the DCT than they are in the neural network that's trained on a mean absolute error loss function. We have ways that we can improve this, but I'll show that in some future slides. So this is the baseline. And so the next thing that we want to show, now that we've demonstrated that, for any given pixel, our neural network has the same chance of being right as the DCT, but the finer variability is better captured by the traditional technique than the neural network technique. We can sort of, after having done that sanity check, we can take this technique to its limits. So I'm a laboratory scientist by training, and so of course we have to consult the experimental literature. And this is a physical simulation of the compressibility limits of many channels of post-it note data, which is just a joke. And it's actually just a fun demo from one of my favorite YouTube channels, but it's still a decent analogy for the compression problem for satellite data. And with post-it note data, like satellite data, especially for the alerting use case, it's okay to lose a little bit of information around the edges, but we don't want our answer to blow up. So if we flip the problem on its head a little bit and say, okay, what is the typical max compression ratio for these DCT techniques? And based on having these blocks of basis functions, the typical allowable compression ratio is about 144 to 1 before you start getting things to behave very, very wonky. And the mean absolute error, if we use DCT to perform a 144 to 1 compression ratio, is about 3% mean absolute error. And so if we flip the problem around a little bit and say, what is the compression ratio for a neural network that achieves the same mean absolute error as this 3% DCT at 144 to 1? And the amazing answer is we can achieve a compression ratio of 2048 to 1 and still maintain that 3% mean absolute error. So we get a 14 times higher compression ratio than a traditional technique for the same amount of error. And 2048 to 1 is a pretty extreme amount of compression, but here's what that result looks like. 3% MAE max compression, here's the original. Here's the neural network compressed down to a factor of 2048 and then reconstructed. So significant space saving, but you lose a lot of the fine scale details. But if you're looking for where there might be feature of interest, or this is a semantic map that you're segmenting here, and you're looking for places to focus or not to focus, this still gives us most of the information we're interested in. And comparing that to a much less compressed DCT, this is what it would look like if you did 144 to 1 compression, which results in the 3% mean absolute error, but a lot heftier payload if we wanted to downlink that one. So the neural network results at these really high compression ratios are pretty promising. And so next we want to ask how we might improve the texture, that issue that we saw where the DCT was pretty good at the lower compression ratios, but the neural network was still showing blurrier results than ideally we'd want to see. And so the approach we use to overcome the blurriness is called adversarial training. So we pit our autoencoder against another neural network that'll help it learn how to reconstruct and capture the high wave number information. And so this discriminator network that we train adversarially against our autoencoder is a fully convolutional patch GAN, which only has access to that high wave number information. And so basically it looks at the fine scale textures of either a real image or an image output by the autoencoder. And when I say image here, I really mean 16 channel data cube, and tries to decide whether the fine scale texture is realistic or not, or matches the input distribution. And GAN loss here is proportional to some factor times the L1 loss, which is our MAE, and a linear combination of that and the discriminator loss. So how well this discriminator determines where the autoencoder does a good or bad job at capturing the fine scale detail. And typically we weight the L1 loss much higher than this discriminator loss. And if we look at some early results for this adversarial training, we have the original image that we input, we have the neural network reconstruction, and we have the DCT. And we see that in the adversarial training case, we do a lot better at reconstructing the fine scale detail without introducing the additional anomalous power at the low wave number, or at the low length scales of the high wave numbers. And so these are promising results for an initial look at this 32 to 1 compression case. And so we're still working on the expanding this to the high compression case with the adversarial training. And so with that, since we're running low on time and I want to leave some for questions. The conclusions that we can draw from this type of investigation include an autoencoder can achieve a much larger compression ratio than DCT for a comparable mean absolute error. What this does, combined with the ability to do inference on board a satellite, is that for our Horus satellite, it'll facilitate the ability for us to do hyperspectral data processing within the limited swap of a 1U CubeSat form factor, and allow the CubeSat to tell us what it sees when we care, or we are interested in being alerted on something that's mission critical and timely, rather than having to wait for the whole image or the whole data cube to be downloaded for us to for it to show us what it sees and make a decision on the ground after whatever amount of additional latency we've incurred there. And we've also proven, at least for the lower compression ratios, that adversarial training can indeed improve the texture without adding significant amount of low length scale variability. And so next steps are continuing to optimize the model to allow it to train effectively on the highest compression ratios. We want to take this model that we've trained on GOES data and transfer learn the model to be able to perform inference using the Horus sensor suite, so the hyperspectral suite that we are specifically going to have on board our own satellite. And eventually, our proof of concept will end, we hope, with a full demonstration of on-orbit AI compression and alerting demonstrated with our Horus 1 satellites. That's planned to go into space at the end of this year or the beginning of next year. And with that, I'd like to thank everyone for their attention and sticking with me at the end of the week here. And thanks to NCAR and Sissel and the organizing folks for this conference. Thank you to Azure AI for Earth for computing resources for the experiments. And thank you for Darren McRae and Lisa Graziano for helping with the data processing and the slides. And with that, I can stop sharing, I think.